Hi, my name is Kruthik, and this is my lab on the motion of a falling object. The objective of the lab was to observe the motion of a falling object and compare it to two models, one being the motion of an object that's only affected by gravity, and the other being the motion of an object affected by both gravity and drag force. Well, why is this important? Well, Newton's second law tells us that the net force of an object is directly proportional to its acceleration. Well, when net force is not equal to zero, the velocity of an object with constant mass will be updated by the acceleration due to the net force, as the momentum is also changing. And this can be written using the velocity update formula seen right here. The net force of a falling object can't be zero due to the force of gravity acting on it, and this is called the weight force of the object. There's also a second force acting on the object called drag in the opposite direction of gravity. This drag is caused by friction between the object and the air molecules around it. The net force of the object can reach a point where it is zero, called terminal velocity, where the weight force is equal to the drag force. It's called terminal velocity since the net force is zero and the velocity is constant. So how do you calculate net force, weight force, and drag force? Well, net force is calculated by adding weight force and drag force. Weight force is calculated by multiplying mass times the acceleration of gravity times the unit vector of the y-axis in the negative direction. Drag force is calculated by multiplying the proportionality constant by the magnitude of the velocity squared times the unit vector of the y-axis. So here's my model and tracker. I dropped a paper towel roll and used this calibration stick for a reference for the height of the drop. And I tracked each frame, and you can see that right here. And you can see the data on this graph right here, as well as it being outputted right here. And I then inputted this into Excel to compare it to the other models, which I'll show you right now. So here's the model for the gravity-only model. Here's the code for it, and you can see here the mass was inputted right here, 214 grams. The initial velocity from tracker was inputted here. The initial position was inputted here, and the initial velocity was 0. And here you can see the acceleration of gravity as well as the unit vector for the y-axis. So for the gravity-only code, the proportionality constant was 0 as only gravity was acting on the object. And you can see that the net force calculations here, where you can see the weight force calculated here and the drag force calculated here. And for the gravity-only code, the drag force will be 0 as the proportionality constant is 0. And you can see the velocity update formula here and the position update formula here. And here's the model for the gravity-only code, and here's the graph that was outputted. And here's the code for the gravity plus drag model, and the only difference in the code here was that the proportionality constant was changed to include drag, and I found this proportionality constant by running the code until the final position was equal to the final position in tracker. And this proportionality constant changed the drag force here, causing two forces to act on the object, and this caused the net force to change. And here's the model for the drag and gravity here, and here's the graph from that. So once all of the data was inputted into Excel, I was able to graph it, and here you can see the observed model in orange, the gravity and drag model in gray, and the gravity only model in red. So the gravity-only model was the fastest, with the position not flattening as the curve goes along. The gravity and drag model was the second fastest, with the position flattening along as we go along the curve. And the observed model was the slowest, with the position also flattening out as we go along the curve. So the position and the gravity and drag and the observed models are the slower ones because they included drag in their models. And the gravity was the fastest as only gravity acted upon it. And the discrepancy between the gravity and drag model and the observed model is likely due to human error, as the paper towel had an angle towards the end of its drop, causing difficulty in tracking using tracker, causing there to be error. So for future studies, I'd drop the paper towel roll many times and average the tracker data for a better observational model, and I'd also be more accurate when tracking the object in tracker. I'd also determine a better method for finding the proportionality constant for the drag, so the model would better describe the observed motion. So what does it mean? So when you examine velocity versus time for the predicted models with and without drag, is there a terminal velocity for either of the models? Well, when I compared the gravity-only model to the gravity and drag model, the velocity continued changing in the gravity-only model, but reached a constant -8 meters per second in the gravity plus drag model, meaning it reached a terminal velocity when I extrapolated both data sets to 2.5 seconds. So this means that for the gravity plus drag model, there's a terminal velocity point where the net force is 0, meaning the weight force is equal to the drag force. So if there was an initial velocity when the object was thrown downwards, would the terminal velocity be different? So to calculate this, I changed the model by including an initial velocity right here of -1, and the only difference was that the object that with an initial velocity reached terminal velocity slightly quicker, and the terminal velocity was still -8 meters per second.